coming to learn more about Karst. Before we get started, the Kickapoo Reserve Management Board would like to acknowledge that the state and federal lands that comprise the reserve fall within the ancestral homelands of First Nations people, including the Ho-Chunk Nation. We recognize the sovereignty of the Ho-Chunk and other First Nations, and we'll work towards a shared future by continuing to create collaborative opportunities to protect and preserve these lands. The Driftless Dialogue programs are made possible by a grant from the Ralph E. Newsom Kickapoo Reforestation Fund, administered by the Eckerd College of Agriculture and Life Sciences, and supported by Friends of Kickapoo Valley Reserve. Tonight, we'll learn what forces shapes this unique landscape we call home. We'll leave ample time to discuss not only what is beneath our feet, but also what it means for us and our many land and water uses. Our presenter is Forrest Jahnke, the program's coordinator for Crawford Stewardship Project. Forrest grew up on Dancing Waters Permaculture Co-op at the headwaters of the West Fork of Knapps Creek. For 13 years, he has served as the program's coordinator, where he has associated and collaborated with the best geologists he can find and done extensive research on the local hydrology. Welcome, Forrest.
Thank you. Thanks for having me. All right, clicker's working. Thank you for the intro and the help with the technology. Always the most stressful thing about these things. So now that we're running, yes, as Amy said, I'm Forrest, and I am not a geologist, so caveat there. But as a kid, I wanted to be Rob Horwich, who was one of the founders of this place, the Kickapoo Valley Reserve, as well as one of the co-founders of Crawford Stewardship Project. He's an amazing biologist, studied monkeys, and created conservation contagion across the world, inspiring communities to protect their landscapes and the special monkeys, or whatever it is that they had there that made their places special. I ended up going to college and deciding I didn't want to bother getting a PhD and becoming a scientist myself. Counting dolphins in Florida was great, but I decided I would rather be the person to read all the studies and try to communicate that to people in a way that is somewhat understandable, because as far as I could tell, that is a great need in our times. We have so much information out there, but actually integrating that into our lives can be very challenging. So I switched to communications and international relations, global affairs, and Spanish major, and totally flipped my career, but I ended up coming back here and getting a job 13 years ago with Crawford Stewardship Project, reading as many scientific studies about this area as I could and trying to explain it in as simple terms as possible to people. So that is what I will be doing. Again, with the caveat that I myself am not the scientist, but I have access to excellent scientists and piles of documentation for all these things that I'm happy to share. My contact information is out there broadly. So the theme of the day is Driftless Karst, and that is what we are standing on. That is this area. Those are two important terms we'll be diving into that describe this special area. So first of all, what is karst? I feel like the term is finally getting a little bit more understood out there bit by bit, but it is kind of a weird term. It's a Germanization of Kras from the Slovenian Kras Plateau, so it's a little bit of a weird etymological history, but basically it's ancient carbonate bedrock. So the carbonate bedrock in this area is dolomite, largely. Limestone is another carbonate bedrock, and very old. And then the second part that's important here is that it is dissolved by the water flow. So you may know of acid rain. In fact, all rain is acid rain. It's just acid rain happens to be particularly acidic because it's falling through more polluted air, and that creates more interesting acids. But any given rain is slightly acidic because of its passing through the various particles. It creates carbonic acid as it passes through carbon dioxide, and even a very weak acid is enough actually to dissolve this rock, which I can demonstrate here quickly. This is a little limestone fossil. I'm going to drop some acid here, and if I pass this around, you can see I took that from Professor Kelvin Rodolfo. I don't own that one. He always used that one.
Is that vinegar you put on there?
It's a little bit stronger than vinegar. It's like a cleaning muriatic acid, so it makes it a little bit more dramatic. This is an accelerated version of what happens in reality. These are incredibly slow processes, but basically you can see from the bubbling and foaming that that acid is reacting with the rock, and that is how it forms all these really complicated features underground, and they can be little fractures or big caves, and we'll be getting into that more, but the third and final important point is that it is just very complicated. So how this formed, and we're talking about a few different layers in this area. We have what's called a layer cake geology of different bedrock layers. And it was created a long time ago. The relevant layers we're talking about are the Jordan and Cambrian and Precambrian sandstones going up through the dolomite here, and maybe we have a little bit of the St. Peter sandstone in the uplands here in Vernon County. So we're talking about in the range of a little bit less than 470 million years ago to about 500 million years ago as these various bedrocks were deposited. And the reason they are different bedrocks is because of how the sea, this area was a shallow tropical sea at that point, and when it was shallow, which it was for much of the time, it was these shallow sand dunes, basically, and these wind-blown dunes. The sand would blow around, and it created these really well-rounded sand particles that created these Cambrian and Precambrian sandstones, very high-purity silica, well-rounded balls, which also makes it good for frac sand and also makes it one of the best aquifers in the world. If you think of like a bucket of marbles, you can fill up that bucket still with a lot of water because of those well-rounded, well-sorted grains of sand. So we have an excellent aquifer here because of that sandstone layer. And then the carbonate layers, or the karst layers that we were talking about, those were formed when the sea level went up, and basically were formed from the dead bodies and shells and slimes of all the various creatures living in the ocean at that time. There was not a lot of life on land, but there were all sorts of things. I mean, I just passed around a fossil of one of the creatures that was living in the oceans at that time. Some were tubular, some had spirals. If you walk the washes and pick rocks around here, and they have some various rocks around here as well, you'll find some fossils like that. Mm-hmm.
Is there any sort of a thought given to, was the world encompassed by water at one time?
So this area particularly, because of the continental drift, at that point in time was pretty close to the equator. And then over time we've shifted to the north to where we are now. And then, I mean, in that amount of time, in the 500 million years, there have been glaciations that have pushed the shelves down, then it kind of goes back up, and then they smash together and form mountains. So there have been a lot of changes. At that point, I think we were post-Pangea, but still a lot of action going on, and things looked nothing like it looks here now. There's very little life on land again. So that's the formation of these layers again. Deep water laid down the carbonate bedrock, shallow waters laid down the sandstones, and it created these flat layers of different bedrocks. And when we're talking about the bedrock stack here, higher you go is younger, and the deeper you go is older. That's generally how things operate in geology, although as you can see here, there's weird exceptions when things get pushed up or things cut down. Actually, when the Prairie du Chien dolomite was deposited, sea levels then went down for a while, and there were a couple million years of paleokarsting, so those hills actually were carved into by millions of years of erosion and dissolution. So this layer of the Prairie du Chien dolomite, you can see how the St. Peter sandstone, it has this big cut down, so that kind of represents that, and that's why, like on our property, we can dig a post hole here and be digging through clay, and then 10 feet away we're digging through sand, just because, you know, that was some valley or canyon back in the day where the dolomite got cut into. So there's places where the St. Peter sandstone is 100 feet thick, and there's places where it's almost non-existent. So it's kind of a simple layer cake, but it's also complicated by paleokarsting and all sorts of other fun things like upwellings of mineral-rich fluids that gave us the various metals we have around here at various levels as well. So we can move along, again, getting back into the karst and the carbonate here. These are some of the features that you can see on the landscape with sinkholes, blind valleys, streams, and you know, the sinkholes and blind valleys we can see on the surface, those just being a reflection of all this complicated business going on underground. This is just a picture of a local quarry, which are excellent places to go to see a cross-section of what the bedrock looks like. And you can see here what's represented here. You've got these both horizontal and vertical fractures throughout. A lot of times towards the surface, there's a lot more of them. And then as you go deeper down, there may be fewer, but they tend to get enlarged even more because it funnels more and more water through, more water flowing through, dissolves it even faster. And so you can get some pretty dramatic features. So some of the surface features we see all the time, sinkholes. This is a particularly large one that could swallow multiple school buses. It's also quite old. You can see there's trees growing out of it, so it hasn't collapsed in quite a while and has these sort of gentle sloped sides, as opposed to a fresh sinkhole will have raw vertical sides. And I mean, there have been people who have literally fallen into a sinkhole in their backyard around here, or tractors that have fallen into sinkholes. Caves are another one that we know. These are just the ones that happen to open to the surface, and we have lots of them. I wish I had a map of all the caves, but we've been protecting the caves so that we protect the bats. So I respect that, and we keep most of our caves secret. But there's lots of caves around here, and again, these are just the ones that open to the surface. There's a lot more that we don't know about. Springs are another classic surface karst feature. They can come in various forms. This is Croom Spring in Vernon County, where the water is shooting directly out of the rocks. And then this is actually from our community where I grew up. This is why we're called Dancing Waters, because we have this very large spring where the sand is just constantly churning and bubbling up the water. And springs are great. Also, don't assume that the water coming out of them is good just because it's a spring, and springs are amazing. It is the groundwater becoming surface water, so it's probably the safest surface water you can drink. That said, know the land uses around it, and probably don't drink out of them 24 to 48 hours after a major rainfall. Our spring will go murky, and we've tested it. Normally it's very good, and I've drunk from it my entire life. So I don't want to discourage people from doing that, but just be careful. So where is there karst? This is not unique to this area. In fact, almost a third of Wisconsin has karstic bedrock, about 20% of the world. So there's, Florida is very well known for its karst. You can see pretty much the entire peninsula is a big limestone slab. And then in Wisconsin, it's a little more complicated. This is Florida. They're well known for very dramatic sinkhole collapses, more dramatic than around here. because, again, they're this solid limestone slab. All those underground caves in Florida back in the day, Florida used to be one big swamp and they were all filled with water. We drained the swamps, we put in golf courses and these sorts of landscapes, and next thing you know, Porsche dealerships are falling into sinkholes because we emptied all that water and the hydrostatic pressure keeping up the cave roof was gone, collapse, and yeah, there's probably $3 or $4 million worth of cars in that sinkhole. And you can see there's even another small hole here, so it'll like collapse in and then it'll flush down farther. And any sinkhole, even a small one, is a collapsed underground cavity. So a significant void underground has collapsed to create even small sinkholes. This is Madagascar karst, so much more ancient karst than we have here. But you can see, again, these same sort of vertical and horizontal fracture patterns that tend to form. And we could have places that look like this in the Driftless, give us another few million years. But we'll see if we last that long. So zooming into Wisconsin again, this here is a cross section. This is showing all the different bedrocks in Wisconsin, of which there are many. But I think what's worth noting here is this orange section here. This is the central sands. This is a thick block of sandstone. And again, that's all of our principal aquifer, an excellent aquifer, as I mentioned. Underlain by this red is solid granite bedrock, crystalline bedrock. It doesn't really hold much water. But we have this really nice thick block of Cambrian and Precambrian sandstones, on top of which we have these various layers of the dolomite, another layer of sandstone, and then the limestone on top of that. So it gets really complicated in here. Out here, this is a well-known karst area, the Silurian dolomite. They actually have additional protections there on any sort of spreading or storage of manure and nutrients because they were recognized as being particularly sensitive. That said, you'll notice on this stack here, this is a younger layer of carbonate bedrock. These are older layers of carbonate bedrock. The older the layers, the more chance it has for these karstification processes, for this slow dissolution of the bedrock and forming all these different features. Here's another map of Wisconsin, zooming in just on the carbonate bedrock. Another difference between western and eastern Wisconsin karst is in eastern Wisconsin, this says over 50 feet is the tan. So there are areas in eastern Wisconsin that still have pretty thick soils, more than 50 feet of soil to bedrock that will do a lot of good for filtration of nutrients or chemicals or anything going down. Whereas out here, if you know anything about this area, there really are very few places that have more than 5.5 feet, 6 feet, 10 feet to bedrock, except the deepest valleys. So we have relatively shallow soils out here, so the bedrock influence is pretty notable and important. So we're still zooming in a little bit more here. Again, these are the 4 main layers that we're talking about, the green being that Jordan, the Cambrian and Precambrian sandstones. The orange on top of that is the dolomite. On top of that is the yellow St. Peter sandstone. And on top of that is the Platteville Galena limestone. So red and orange are both karst, and yellow and green are both sandstone. So you get these really interesting interfaces of these different bedrocks. This data that I'm showing you here is from the 1870s, so it's literally Civil War era bedrock data. Mr. Moses did an excellent job with the technology of the day, and I'm sure those mules did a great job too. We have better technology and better maps now. They're just still not quite available yet. They keep telling me next year. So hopefully by next year, we'll be able to show you much more detailed maps of these bedrocks. This is a map of the slopes of the area. So this is the other influence we have here, the driftless part. We have flat layers of bedrock, but why does the bedrock map look like this if it's flat layers? Well, because it's not flat. Because that got carved into by 500 million years of erosion, essentially. And the whole surrounding area, all this black area, black is flat, and then the lighter green, you get the steeper the slopes. So you can see all of this is essentially an 18,000-year-old landscape. This is a 500 million-year-old landscape. And that makes all the difference, as you can see, looking out here. But you can also tell that it was flat at one point. These layers were flat. If you go to the highest ridges around here and look around you, it's a flat horizon. But if you're in a valley, it's hard to say it's flat. It's all about perspective. Mm-hmm. So some of the things we can do with some of the more recent data we have available. This is a LiDAR, is the base layer here that you can see is much more detailed than that bedrock mapping. So in Crawford County, we had some citizen science events where we actually mapped over 450 sinkholes of at least 2 feet in depth in Crawford County. Not a comprehensive mapping, I would say. For each one of these points, there's probably a dozen more sinkholes at least. The best evidence of sinkholes is other sinkholes, because again, if there was a cavity underground big enough to collapse and form a sinkhole, you can be sure there's a whole lot of fractures going on all over in that area. But it is interesting to see that, and then we actually took that same data and made a heat map out of that, so you can see that there are areas that have far fewer sinkholes. You're much less likely to be on top of a sinkhole, and like here in Seneca or Central Clayton Township, there's some pretty significant clusters of sinkholes, and in any given area, you're probably sitting on top of some pretty significantly fractured bedrock. This was just done for Crawford County because that's what we had the resources to do, and we're a small nonprofit. We are still trying to interest the state agencies to do more study. That's another underlying theme in all this also, is that there's just not enough study of a lot of these things, and it'd be really great to have more. This is another thing that Professor Kelvin Rodolfo and I did. We actually mapped the fracture patterns in the area. So this tan here is the Prairie du Chien dolomite that kind of has two principal directionalities, one kind of east to west and one north-northwest to south-southeast, or yeah. And then here in the limestone, it's a little bit more complicated. It's higher up. It has a lot more fractures in it. But this is the kind of stuff that Kelvin can just read, like people like us can read words on a page, and it's pretty amazing. And influences both how water would be suspected to flow underground along those lines. Also, it gives this landscape not just the pure dendritic form, like you think of a tree or our neural networks, they form like these dendritic drainage patterns, but it's not purely dendritic, it's both dendritic and trellis patterns. So you can see like there's a lot of hills and valleys that tend to go straight east-west or along these lines. So it just adds another interesting layer and informs us how water can flow. This is zooming in on the LiDAR a little bit more. You can see again there's pretty good detail. Those green points are again the sinkholes that we identified. This was an area that we wanted to monitor because there was a proposal to produce and spread 10 million gallons of manure there at this point. So we used this LiDAR data that we had to choose our water quality monitoring sites based on that. So this is the point we're checking, and the spreading is going to be around here. Point F, which we identified, gives us this watershed area, and these lines are watershed boundaries that are mapped. This is all publicly available data. And then point G gives us this watershed here. And then we also added point H because there's a spring here that's outside the watershed and is only fed by this tiny little micro watershed. So that's kind of our control point and would give us what groundwater should look like coming out of that point. And this is along the Kickapoo, the lower Kickapoo River. So this is some of the things we can do with that LiDAR data and just that really detailed surface topography that it gives us. It's really cool technology. They've actually flown this area twice, once in 2011 and once in 21. And they take this laser imagery that strips off the surface vegetation with some algorithms and gives us incredibly detailed elevation data with which we can do things like identify sinkholes and find strategic water monitoring points. Here's some of the water quality monitoring in the area. This landscape presents unique challenges for that because, well, sometimes we don't have permission to go on land, so we do from bridges, and we've got our sophisticated monitoring tools like PVC pipes and cords and things. Sometimes streams are very shallow, and at this point we're actually using a syringe. Rick is holding a large syringe here to slowly suck the water up so you don't get too much sediment because it's only like an inch deep there. And this is pre-COVID. We were wearing masks before it was cool because there's all sorts of nasty things in that water that we didn't want to expose our volunteers to. Which, because of this complicated landscape and anything that we spread can get on into the water, here's just quickly some of our results that we have been finding at our different sites. The health standard, or where things should be for E. coli at 100, per 100 colony forming, per 100 milliliters, is 126 colony forming units. So that's way down here at the bottom. And some of these spikes go up to 17,000. They go off the page here. You can't even see the top of the spikes. But generally speaking, we do see E. coli much higher than the health standard. The purple one here is actually a spring, and even the spring does pop over the E. coli sometimes. A lot of that is influenced by rainfall. So a lot of the spikes on there were caused by major rainfall events. But even in the dry years, you know, these are droughty years here. What is it, 22-ish, 21, 22, started getting pretty dry, and still even there, because of these steep slopes, because of all these direct conduits to groundwater, there can be all sorts of things in the creeks. This is phosphorus, same sites. Also, you can see the standard line in red at the bottom there, and our results often much higher than that. It's not all scary though. I will say that we've also done a lot of well testing in the area, and in general, most people in this area are still drinking some of the best water in the world. So no nitrates detected in 18% of the wells in 2020, and then in 26, it was actually 27% of wells had no detectable nitrates, which is pretty amazing. That said, we also have, the red dots are over the 10 milligram per liter health standard. So those would be points of alarm, and then black is over twice the health standard. So very concerning results. So there are still people with some issues in the water, and there are people with significant issues in their water, although many people still have very good drinking water. And this was a fall test, and this was a spring test in Vernon, Richland, and Crawford counties. We did collaborative testing with the county conservation and health departments. And this last year, we actually got a whole bunch more parameters tested, including all the metals. There's a couple black binders back there that have all the different results. If you want to flip through those, you can check out all the different parameters There's lots of interesting ones that we don't have time to get into, but nitrates is kind of the primary one that we look at in drinking water for well tests. And if you have high nitrates, it means that things from the surface are getting into the groundwater and into your well, which again is just very varied. It can change one hill over. And this can be correlated to land use. That's one of the correlations that has popped out in the drinking water testing that we've done. So between geology and land use, you can pretty easily explain, especially the high nitrates. If I flip back here, so our little cluster of very bad results here, 3 over 20 and 1 over 10 right down there, are all in these very heavily corn, soyed, and irrigated fields on top of an unconsolidated gravel aquifer down here in the lower Wisconsin River. They have not just those layers that I talked about earlier, but when glacial Lake Wisconsin popped and flushed this river through and actually reversed the direction of the Wisconsin River and blasted through Military Ridge and pushed the Mississippi down that way instead of that way, it deposited all this gravel and sand in the broad valley down there, which makes it very well drained, very productive, excellent farmland, but also things that put on the surface can easily get down into the bedrock. Also here you can see in Vernon County, this area here where there isn't really anything that is unaffected and there's some pretty significantly high results, also just happens to fall in those rolling uplands where it's kind of seas of continuous corn and soy. So those tend to be the largest risk factors and show that we have to be very careful with our land use around here. And there's different ways that the land can be used to produce food. We hope that this land is still used to produce food for people as well as for its natural beauty. Both of these landscapes are producing food for people, but one of these land uses is capturing a whole lot more nutrients and doing a whole lot more filtration with all these diverse roots and permanent living cover. But you see here, there's really only these little lines of green, and nutrients that are on where there aren't roots are just going to go down into the soil. And if there's thin soil on top of the carbonate bedrock, they're just going to keep going down until they get into the groundwater. So this has implications really for anything that we do. And Crawford Stewardship Project has been working on this issue regardless of what we're talking about. Of late, the high capacity transmission lines have been the big thing. When Crawford Stewardship Project formed, it was large confinement animal operations. There have been frac sand mines proposed, and there's been lots of things, but we really believe that this information is critical to understand no matter what we're doing, even if it's just building a house, because you probably don't want to build a house on top of a void that it could fall into. So these are some of the sources. Again, we have lots of additional sources on top of this, but this is a few of the main ones, and just a few things that we can do. All of us can do things to help keep our water safe and drinkable. Knowing the land you're on is a pretty clear one. I don't think it takes a lot of explanation. Testing our wells is clearly important because those are really the information points we have for the groundwater at all. Otherwise, we have no idea what's going on down there. Monitor a local stream, so checking the surface waters as well. We've been working with the Water Action Volunteers program through state DNR to test the streams, and then we do a whole bunch of extra testing on top of that. Show up with information, so there's lots of processes going on all the time, your township meetings, your village meetings, your county meetings. Most people largely ignore these processes. You have more of a voice at these places than you do in the state and national politics that we tend to stress out about all the time. Show up with information, and I also, this isn't to say show up and start yelling at people that they're doing a terrible job and need to stop this scary thing that's going to happen. I actually recommend that you show up and don't say anything maybe the first few times, and get to know the people who have been elected to be your representatives and are doing their best job to do things well as well. Note and protect karst features. I think that just goes without saying, given what we talked about. All of those karst features are just these direct funnels into the groundwater, so we have to be extra careful there. And then slowing the flow is a basic concept that we should be using in general. The Coon Creek watershed mantra was make water walk, not run. So following those same principles, basically, if it's moving more slowly, that gives the soil and the bedrock time to mitigate things. Whereas if it's running through these fractures very quickly, it doesn't have time for that mitigation. And here there's some just practices: maximize permanent living cover, rotating livestock on pasture, planting and encouraging deep-rooted perennials, maintaining buffer strips and contour cropping and terraces, cover crops, all sorts of things that can be done. This area has been a pioneer in sustainable agriculture for a long time. We are just outside the headquarters of Organic Valley, the largest producer-owned organic food pool. So, as well as lots of other cool and inspiring initiatives. The Great River Grazers is a peer-to-peer group that's been teaching each other how to pasture well in this area for almost 40 years now. And there's a whole bunch of excellent pasture walks and educations going on around that. So yeah, just generally stay calm and take action. So don't let the big issues of the world paralyze you. There's a lot going on, but all the emergency step-by-step response things I've seen, whether it's a hurricane or an earthquake or a tornado or whatever, the first thing is stay calm. So let's try to do that. We're all neighbors here. We all like each other, or even if we don't, we're still neighbors. So, we'll work through things as we need to with whoever's making the decisions. And yeah, that's mostly what I wanted to get out there. I really wanted to make sure we had time for ample question and answers, so I blasted through a lot in a very short period of time. Feel free, any clarifications, or I'm also happy to talk about whatever specific issues people might want to touch on or dive into some of these other things. In the meantime, you'll see I stuck some dye in these groundwater simulators here. One of them is a sandstone model, and the other is a karst model. So this will show some of the differences in how the water and various things that go into the surface and get into the bedrock, how they react and how things flow. This one's been in there a little while already and is just kind of starting to create its plume and move towards the river, and this one has already penetrated most of the bedrock. So that's a dramatic demonstration of some of the surface flow. And then with this one, you'll see how it's slowly, basically it's all going to move towards the low pressure point here and come out in the river. And you'll see how a lot of times groundwater does not actually just move down. I mean, we think, the rain falls, it soaks in, it goes down until it hits the saturated zone, until it hits the water table. Once it's solid saturated water, it can move in any direction. It's going to be mostly moving horizontally. Here it's actually moving vertically upwards into the river, which I guess I was taught in school at some point, but did not really sink in until we got this model and I started showing it to people. So these will just be happening slowly in the background, and you can observe and reflect as they happen. And in the meantime, I'm happy to answer questions. Huh?
If you would talk about your handouts, this is a really excellent handout. At the table back there, I don't know what else you have there, but this is really a very good handout.
Thank you.
Talks about all that stuff.
She's not a plant, but that's exactly the kind of questions I like to see. Yes, we have lots of information back there. That sheet she just held up, we created and is specifically on this area's karst. There's also some state information on the bedrock. We're advertising an event, our next karst exploration, which Crawford Stewardship Project holds every year. We'll be at Sugar Creek Bible Camp on August 15th. We're going to have a Springs study report from Chloe Fandel, Eckerd College. They did a spring study last year and got some really cool information on that. And then we'll be walking around and checking out some of the springs in the area. As I mentioned, there's the maps of the well testing, and also you'll notice there's the karst cutaway poster and the Driftless slopes map, some of the images that you saw here, which are available in the gift shop for $10 a piece. Yes, okay. Mm-hmm.
I can remember an extension agent telling me about an instance in Door County where a restaurant was having problems with coliform in its water. And they took some blue dye and put it in a septic field. And the next day the blue dye was in in your drinking water. That just kind of explained to me how fast water can move through karst.
Mm-hmm. That's an excellent, and I don't know of any dye tracing that's been done in this area, but it's an excellent way to see those connections. Just across the river, Luther College did a dye tracing study where they poured some of these hardcore dyes into a bunch of sinkholes and then monitored which local springs they came out in, so you can actually trace the underground flows that way, or yeah, into the septic system is a very good one. Well, it wasn't a very good advertisement for the restaurant, so yeah. Mm-hmm.
There was a slide, maybe the 8th slide or so, it was zoomed in on Wisconsin, and on that map, there was some lines, I'm colorblind, but they were speckled, and they were pretty uniform and ran fairly straight. I just wondered what those were. I was trying to look at it as we went.
This one, or?
Go back quite a few more. It was the whole state.
This
Right
one?
there, those
Yeah.
lines, those speckled lines that run maybe from like Marshfield down to northern Crawford County or something.
Yeah, so these,
Yes.
I think this would be what's called like the moraine areas. So the glaciers came through, and then when they receded, they kind of left on the edges of the driftless area some of the moraine terrain, which is not flat, but not driftless either. Mm-hmm.
I wonder about the LiDAR thing.
Mm-hmm.
How could that depict such a broad scale? Do you know anything about LiDAR?
Yeah, so they did flyovers with airplanes with these little laser rigs on them that took...
Can penetrate the surface?
They don't penetrate the surface, they hit the surface. What they do is they take so many readings, and they only take the deepest readings, and then they go through with an algorithm that allows them basically to strip off all the surface vegetation. So it's a perfect visualization of just the land surface without all the trees and shrubs.
That's built right into Google Maps and all your
Right? Yeah, Google Maps has it's not as good a quality as we have here, but yeah, there's lots of very good things available. Also, on our website, we have our karst geology viewer, or karstology viewer, to make up a word, where a lot of these layers are available. If you click to learn more, you can read about the whole process and how we came up with these things. A lot of it is focused on Crawford County, but the hillshade here, that is the LiDAR. The hillshade is just how they call this depiction of the elevation data, because it's as if there was sun hitting it at a certain angle. But all sorts of very interesting things you can see here. And we have Vernon, Crawford, Richland, Grant, Lafayette, Iowa counties all downloaded on this geology viewer. And you can zoom in quite far on this at like a pretty remarkable level of detail.
You said that's on your website?
Yep, that's at crawfordstewardship.org on our Karst page. Here I'm just zooming into our community here, and you can see just the level of detail here. This sinkhole actually right up here on our hill was not even identified by our methodology. And there's another little, even smaller one right up above it that I also suspect of being a sinkhole. And this is the case with so much of the data around here. You can look at the springs data around here, and I can point out 5 to 10 springs on our 130 acres that are not listed on that data. Same with sinkholes, same with many things, because as Kelvin Rodolfo would say, Southwest Wisconsin's been sucking hind teat for scientific funding for a long time, to use farmer terminology.
I think that LiDAR, do you see a lot of it? I see on Facebook a lot. They use LiDAR to determine where the Indian mounds are.
Yep.
And it's very distinct on LiDAR to see the shapes of all the
That's also another secret data set. They don't want you to know where the Indian mountains are.
Yep. Yep. Well, it's great for that, and you can find a sinkhole or a mound on your property that you would have missed for 30 years walking the same spot just because of the nature of this landscape, because it is the result of 500 million years of erosion. You can read the landscape really well, and then you note things like that hole that, like, what is that doing there? You know, or what is that line doing there? You know, that's, okay, this is human activity. But basically anything that is not perfectly drained is the result of human activity or underground collapse in the area, which is how we were able to do all this sinkhole identification just with some algorithms and a bunch of citizen scientists. Whereas in Grant County it would be a little more complicated, because then you've got the additional layer of mines. They had all these mines in Grant County, so some of the holes are for mining. And then get outside the Driftless area, there's closed depressions all over the place because that's what the glaciers did. So just the nature of the really well logically drained area that we're in kind of allows us to do some of this investigation as well. And we've got all sorts of layers on here that are fun. You know, depth to bedrock is an interesting one. As you can see, there's, you know, everything green is less than 5.5 feet to bedrock, so all pretty shallow. This here is the watershed and subwatershed data, and it basically divides the lines along the ridge top. So everything on this side of the line is draining this way, everything on that side of the line is draining that way. Another fun layer, we've got that for the whole state on here. Carbonate bedrock, although again, that is, once you overlay it on top of the hillshade LiDAR data, you can see how old and inaccurate it is, and it doesn't even really make sense to depict it at that scale. If you zoom out, like, okay, there, that kind of makes sense. But yeah, it's kind of like Who Framed Roger Rabbit, you know, cartoon with live action thing going on. But again, I'm promised that we will have better bedrock data within a year. This is like 10 years in that I've been promised this. So I'll let you know if it happens.
It's the wrong county, so it's a dumb question, but the former Badger ammunition plant over by Dartmouth, is that a major source of contaminants or not?
There is a group, Citizens for Clean Water Around Badger, CSWAB. Laura Ola has been following that for a long time. They've done excellent work monitoring and documenting. It's my understanding that things are getting better slowly. They have opened up more areas to foraging now, but there are still significant plumes of chemicals there, and there has been a lot of vagaries and silence around some of the data that should be more public. But yeah, if you're interested in that, I'd look into CSWAB. They're a really good organization. Citizens for Clean Water Around Badger. Mm-hmm.
How does the proposed 765 line impact versus geology, especially?
So for those of you who didn't hear that, how would the proposed 765 line impact this geology and groundwater? Well, if they want to do the towers, which seems to be the current proposal, each one of those towers is a large, heavy thing that's going to be creating a lot of pressure at the base there. So that could be potentially risky if they don't know what is under it. So I don't know exactly what they're planning to do, but generally speaking, what's done is like you just drill some boreholes and maybe you go down 20 feet or 30 feet, and if you don't hit a giant cave, then it must be okay. These, we're talking about very heavy towers. I don't have the exact numbers on the weight. Rob, do you have that off the top of your head? It's a lot. It's a lot of steel, and it's a lot concentrated right at the base there. So my suggestion for something like that, or really anything particularly risky on this landscape, would be what's called electromagnetic resistivity imaging, which sounds complicated, but think of like radar that goes through the air. This actually punches through the earth and can show you where there are underground cavities. They actually did this for all of Grant County at a hefty price, but for something like a high capacity transmission line, for these companies that have a lot of money, doing something like that at every single one of these points to ensure that there's not a giant cave under there would be a logical thing in my mind. So yeah, I would really want those kinds of assurances, basically, that impact is not going to collapse for the groundwater's good, also for the project's good. I mean, they don't want their towers falling into a giant cave either. That doesn't help anyone.
I just want to add one of the numbers that you can keep in mind for the penetrations that Forrest is talking about for the pilings. If the towers are at their average distance from Genoa, basically down to Seneca, and then east to Gates Mills in that area, there's about 120 towers. So that would be 4 pilings, 4 drillings for each. So think about close to 500 penetrations of this area that's sensitive. So that might give you some way to imagine the risks associated with it.
Yep. Yeah, and just generally, I mean, they would have a wider right-of-way, so that would involve clearing and land disturbance, and the more land disturbance you do, the more chance you have for things to run off and go down a sinkhole, you know, even if they're not spraying chemicals or whatever, but I wouldn't assume that either. There's a question
You
back
also
there.
have to remember that each piling requires tons and tons of concrete or cement, whatever you want to call it, and they have to keep filling those pilings until the piling is filled. And if you hit a void, where do you think all of that crap is going to go? It's going to go down into the aquifers and the underground streams and contaminate local wells. So I suggest too that everybody do their annual testing of their wells for nitrates and bacteria. So that you have something ahead of time in case this does go through.
Yes, absolutely. Kelvin is very fond of a story on Seas Branch in Vernon County where there's one of these water retention dams that they put up on the watersheds to slow down the waters during the big pulses. And this dam was starting to leak out the sides and get, structurally insecure, and they needed to patch it up. And so they had $1 million budget for grout that they were gonna, inject grout into there until it was plugged up. They went $3 million over budget, blindly pumping grout into a void of an unknown size, and I don't know if it even worked out or not. They could have saved all that money had they done a little electromagnetic resistivity imaging and seen how big of a void was actually down there, and if it was actually practical to be pumping grout down into these things. And bentonite is what they use for the grout, and it should be non-toxic. However, anything we do that changes these flows can have unforeseen repercussions. Even just a large impermeable area that then flushes more water and sinks more water into another area can cause something that was filled with clay to flush out, and then a new sinkhole appears. Or again, upstream of one of these other check dams that was put in Seneca, they put in that check dam, which means more water is infiltrating in above that dam, and then suddenly a line of sinkholes started popping up, brand new sinkhole in a line right upstream from that. So, these are slow processes, but when we do big changes on the landscape and infiltrate more water here or don't infiltrate any water there and do these changes, it can have impacts that are kind of hard to foresee. Because I can talk in generalities about how things are down there, but unless you do this sort of, lots of boreholes or ground penetrating imagery of some sort, we really have no idea where the giant voids and caves and underground rivers are. We just know they're there, and there's a lot of them.
Two-part question here. I hope that if they find a void when they make a borehole for a piling, they can't use it for that question mark. And then part two would be, what is the proper way to recap a hole like that if they do find a void to avoid damage later?
This is my Army Corps of Engineers friend asking me some engineering questions that are a little bit above my pay grade. So if you don't know, these are excellent questions to ask the company. How do they plan to act if they find a void? My instinctual response would be, why on earth would you build a tower there? That seems crazy. But everybody's got their own protocols.
The way it changes so drastically, though, you might not know what's 20 feet over in some areas, right? So I doubt it would be on purpose. I gotta be double check.
Yeah, well, and that's
on their side.
and that's the challenge of the boreholes, is it really just gives you one point, whereas the electromagnetic resistivity imaging gives you an area to look at and can go a lot deeper, so it gives you a little bit better information. But that points to the challenge of the information. All our wells are just like one little point in there, and that's where we get our bedrock information or our groundwater information. We just have information from that one point. What's going on around that may be similar, but yeah, it could be dramatically different as well.
Just to follow up on your question.
Yes, thank you.
One of the ways that the process goes through the Public Service Commission is that the developer may not be required to do all of the testing that Forrest is talking about. So if the state doesn't require it, we can't get our lawmakers to change that fast enough, then towns, landowners, anybody, counties can intervene, be parties in the proceeding. And that's not as difficult as you might think. You can actually represent yourself without a lawyer. And one of the classic scenarios for if the state feels like there are risks that are not accounted for by the developer's science, then the commissioners, when they approve it, make it conditional that we would have this electromagnetic thing that would be going for every, in other words, like Forrest was saying, assure the landowners and assure the developers that they're not putting towers in areas that are really, whatever. So there's a practical thing here, but the state won't do it for you because the DNR is neutral on the matter. The Wisconsin PSC is neutral. They're not going to do it for you, but if you intervene as a town or an individual, you raise those standards and request it, then more than likely the commissioners will go along with that.
Mm-hmm.
So they're practical things. I agree, this project is not needed, but that doesn't mean that we also don't take precautions in any outcome to ensure that our water and our lands are protected.
Mm-hmm. And I will gladly defer to Rob on any procedural questions about the high-capacity lines. We have a room full of lots of knowledge, not just mine.
I'm curious. I realize geology is different everywhere, but like as just a generality or reference range, like if you're looking at a well, the stuff going on around it, like is it the circumference of a mile around it that affects the water, or like how far does the water move once it's underground?
Mm-hmm.
Like my well, is that affected by 15 miles away, like a major farm, or is it just like right in our area?
Yeah. Excellent question. Also, as you said, very variable. What I've heard for this area is, generally speaking, the water you're drinking out of your well comes from a quarter mile away to maybe a couple miles away. That's going to be really dependent on where you are in the landscape, though. If you're at the top of a hill and you're at the high point, you're probably getting water from pretty much right around you. Whereas if you're down in the Kickapoo Valley and have a relatively deep well, you're probably getting old water and water coming in from a pretty broad area. So it kind of depends on how high you are, how low you are, and again, what kind of bedrock you've got, and if it's, rushing through an underground river towards your well at, 4 or 5 miles per hour, or if it's running at a couple inches per day through the sandstone. So yeah, depending on where you are elevation-wise, the lower you are, I would think you'd be getting from a wider area, the higher you are from a closer area, and the kind of bedrock you're in.
It's kind of a related question with those models. Is there any kind of scale on those models? Because you can see the red dye that's contaminants that is flowing towards the rivers, but is there a scale of like, okay, this model is built at a scale where that distance from where you put the dye in to that river is 1 mile, or the equivalent of 1 mile, or is it just?
Yeah, not really. There isn't a particular scale here, and these models seem very simple, but they are hand custom designed by a guy in Stevens Point who does an amazing job on them, and it's groundwater dynamics are very complicated. But you can see here, it kind of, things from the surface, they're going to go down as you would intuitively think water would until they hit the water table. So the water table being the line where everything below that is saturated, right? All the pore spaces between the rocks and all the grains of sand and everything are filled with water. And above that there's air or a little bit of water filtering through it. And it's going to go down until it hits that, and then a lot of the contamination is going to stay in the top bit of the water table, which kind of brings us to the importance of depth of well casing, or the depth of your well in general, where if you have a really shallow well, or if you have a well that doesn't have very deep casing and you're drawing from the upper part of the water, you're more likely to be getting contamination than down deeper. That said, digging a deeper well or casing your well deeper does not ensure that you will get clean water either. And there are things that can happen on the landscape that can change how that water is flowing. Right now, the water's all flowing towards the river, but if I start madly pumping out of this well here, and I'll just keep doing that as I'm talking, you'll notice that things will start to change, because I'm creating what's called a cone of depression here, where the water that I draw out of here is actually pulling the water table down sort of in this cone shape here. And we'll start drawing things in the surface down deeper into the water table, as well as I see I'm sucking up some green dye already, so I'm getting what's moved over here into here.
Would that represent a high capacity well?
This is essentially representing a high capacity well. Or honestly, in this area, any well pumping can have pretty significant impact. If you're up high on the watershed and you're in these carbonate layers of bedrock, you can be impacting your neighbor's wells pretty easily. I mean, a high capacity well technically is 100,000 gallons per day, so it's a lot of pumping. Even the large hog operation I was referring to that was proposed that would have been 10 million gallons of manure per year was only going to be 89,000 gallons per day maximum. So, I mean, the high capacity wells are truly high capacity. And there's not a lot of them in this area yet, but there's, this area is water rich, and there are proposals coming in to do things here that would be using the water wealth that we have here. So, things to pay attention to. Mm-hmm.
Is the water table around here getting lower with time, or is it staying pretty stable?
There is, again, not good data on that generally. I can speak to my 37-year experience on my property, and it has actually gone up slightly on our property. I've watched where the water is continually flowing in our dry wash where it becomes a creek, kind of march slowly up and up. I don't advertise that a lot because we are one of the few places in the world where our water table is going up. And again, that is that specific place. We do not have the information to know generally what the groundwater quantity is around here at all. There is not a DNR groundwater monitoring well in Crawford or Vernon or adjacent counties at all. There's some really cool technology out there called Well Intel, where you can get a real-time monitor on your well that will show your water levels. And if a whole bunch of people got those, we would actually have some decent data on our water table levels. And it's all attached to the satellite and updated in real time, and they pump out these reports. And it's a project we'd love to do at some point. If you know of any funding for such things, pass it my way and I'll write a grant for it. But
Have you done any monitoring of plastics,
PFAS is a whole thing. They just finally released the funding that they put aside at the state level. There are some requirements for public systems to be doing PFAS monitoring, so we should have some information on that. We've not done any of that monitoring ourselves, and to my knowledge, very little, if any, of that monitoring has been happening in Vernon, Crawford, Richland counties. It's expensive. They are not cheap tests, so that's part of it. It's relatively new. As far as plastics, Crawford Stewardship Project did experiment with some microplastics monitoring. We had these little rigs called baby legs. They make baby tights. Did you know that? It's a thing. Anyway, we bought baby tights and put it on a bottle, and you like float it through the river, and you catch the things that flow through it, and you pick through it, and it was interesting. We found things. There's like ways to categorize the different types of plastic, but there's really no standard for or anyone to report to or anything to do with that data besides of general interest.
There is no minimum safe level, and any place they've ever tested, there's no place that doesn't have it in their wells.
Yeah, microplastics are pretty ubiquitous, and well, and these are the macroplastics really that we're getting, and even then you can there's like the fibrous things and the flaky things and the granular things, and you can kind of categorize them, and The organization we worked with, Public Lab, no longer exists, unfortunately. And again, there just aren't any standards, so there really wasn't much to do with the data, unfortunately. But it is interesting, and it is important, and it is another thing that is in the water and in our bodies. And there's lots of products that we can avoid that would put less microplastics in the watersheds. There's some products that are literally just microplastics. My mother actually recently bought a thing and then was so horrified by it that it went straight in the trash because it's literally a microplastics washing system. You like rub on the microplastics and it does a miracle washing job, and then all the microplastics just go away. You know, we love flushing things away. Wherever away is, I'm not sure, but I wish there was one that it could just go away. But it goes down, and then it goes across, and then it goes into your drinking water. So.
The model you've been drawing water from, that is the central sands area of Wisconsin, basically, right? I mean, it's full of high-capacity wells, and it's that.
Yep, that would be more or less just what it's running through, a sandstone layer. This line down here is an impermeable layer or a confining layer that water is not going through. So that shows, you know, you can see like this just kind of went straight across and didn't go down at all because of this confining layer. And so if you have a confining layer, this is also a confining layer in this model, that can be protective of groundwater. So like we were talking about eastern Wisconsin, where they also have karst. They also, underneath the karst, have a thick layer of shale, which is one of these confining layers, and that will stop contaminants from going down farther. So if they dig a deep well past that shale layer, they're very safe in their water. That said, this area does not really have any confining layers or any impermeable layers. There is a great spectrum of variability in how impermeable the layers are. So some, even within the same layer of sandstone, some of it can be really heavily cemented with iron and copper and really hard. And then a little bit farther down, it's white and crumbly, and you can just scrape it away with your fingernails. So there's a lot of variability there, but there are no truly impermeable layers in this area that will stop things from going down. And there's something called the Roundtree clay layer that Kelvin is very fond of bashing because it was a study done, and yes, we have clay on the ridge tops, but it was actually kind of marketed in this area as this invisible force field that will protect us from contamination because we got this nice thick clay layer on top of the bedrock, so the things stop going down. But it's just patches of clay. There is no contiguous protective layer. And in fact, the clay is a result of the dissolving bedrock. So it's just an indication of karst. So the more clay, the more chance you have these big voids underground anyways. Mm-hmm.
Probably a dumb question, but how deep does the water table go?
Well, in this area, let me see, we got our, I don't know, we're not on the presentation anymore. Anyways, when we saw the graphic of the cutaway of Wisconsin, right? So we've got the sandstone carbonate, and then that thick block of sandstone. It's going to saturate that whole thing of sandstone, and then underneath it we had the really hard crystalline bedrock, like the granite that isn't really gonna, I mean, that is an aquitard. That is a aquitard being something that retards the flow of water. It stops the flow of water, same as a confining layer. And so that stops it. So it basically goes down until it hits something that it won't absorb into. And then it goes horizontally until it finds another chance to go down, or it finds a release point like a stream or a lake where it can start flowing out and into things. There we go. Just getting the water model running a little bit more. And again, as you see this run in the sandstone model, it kind of has this logic, right? You can follow it once you understand that it's kind of going here. That's the low pressure point. You can see it's got green and red now. It's all coming out here. Whereas in this one, it is coming out here, but how it's flowing is not intuitive at all. It's very complicated. And this is not supposed to be happening, actually. This is supposed to be a protective layer here, but it's actually leaking out the side, going down through this column and leaking into the protected aquifer down here in the model, which is instructive because that's what it's like around here. There are layers that are not permeable, and then it'll just leak out and down and get in there somehow.
You want to address frac sand mining at all?
Yeah, I can. I mean, that was a big deal.
How do you protect the groundwater with that going on? And these days, we're a major exporter of petroleum because of it.
Yeah, and at the moment, fracking has not been going particularly strongly because the price has been low, but as the price per barrel creeps up, there's going to be more demand that's going to make fracking more profitable again. And then there will be more demand for the sand here. It's a boom and bust cycle. That's what we saw here. There was a whole bunch of mines, and now north of here, they're dealing with what to do with all the mines that shut down. There was a lot of consolidation in the industry also. But
Also, they found that they had frac sand in West Texas at underpriced the Wisconsin sand by,
yes.
90% reduction in fact, all the Texas guys said, we don't need more Wisconsin sand, we can just get it right here in Texas.
It is expensive shipping sand long distances. It is a heavy, heavy product, even though our sand is better. But there's this, it's not just me speaking. This is apparently the case, actually. Our sand is better because it's more higher purity silica, nicely rounded balls, like I was saying, that makes also the best aquifers in the world. Some of us would prefer to keep using them as such. But yeah, with the frac sand mining, some of the challenges there, I mean, any sort of mining, you start getting liquids and leaching that can get into the groundwater. And also, they're taking the sand layers, right? And so the sand layers, where it moves through slowly, that's where the water is getting filtered. That's where it's moving slowly and has time to do that process. So if you have this layer cake, you strip off all the sandstone, and then you're right on top of the karst layer with nothing in between. How responsible are they going to be for, putting down sufficient soil and managing it responsibly? I mean, there have been commitments from some mines to, reestablish native prairie. Restoration efforts are notoriously abandoned often, or done shoddily, or just bought out by some other company that says they're going to mine it again at some point. Who knows when? So yeah, it's certainly a challenge, and as anything done on that sort of scale on this landscape, and they have liquid impoundments also, and any sort of impoundment of any liquid on this landscape, again, that pressure buildup is going to force things out or down at some point if there's a release point or a crack. So definitely creates some challenges, and is something we should probably be keeping our eye on, even though it's been a while since we've really heard much from that industry. But what I've heard is if the price per barrel goes over $100, fracking in North Dakota and Pennsylvania becomes profitable again, and there will be a renewed demand for sand from this area probably. Texas doesn't want our sand, as Sparky noted, but yeah.